Good morning. I'm Altaf Hussain, former professor, Department of Chemistry, University of Dhaka, Bangladesh. I plan to prepare a series of lecture on AS and A-level chemistry, and I have already delivered 20th lecture on AS syllabus of chemistry. This is the 21st lecture, and we were talking about enthalpy change. So in the last lecture, that is 20th lecture, there we finished with saying what is standard enthalpy changes. So next slide, we will continue this talking this. So the standard enthalpy change of formation, what does it mean for us? It means that when we form a mole of compound from its element, the enthalpy change in standard condition, we call that standard enthalpy change of formation. And it is been symbolized like this. This is the symbol for standard enthalpy changes, change of formation. Okay, this, when we form compounds from its elements, thus reaction could be, or standard enthalpy change could be either negative or positive. That means it could be an exothermic or endothermic reaction. Here we have an endothermic reaction and exothermic reaction too. So when we form ferric oxide from its element iron, we use oxygen and then we get ferric oxide. And we have to remember about the states. So iron in solid state and oxygen in gaseous state, and then ferric oxide is solid state. The standard enthalpy change of this ferric oxide in solid state for this reaction, or I have to say the formation of ferric oxide, we have minus 824.2 kilojoules per mole. Sorry, I have not this Fe2 should be lowercase, 2 should be lowercase, and 3 should be lowercase 2. This was a mistake. Okay, the standard enthalpy change of combustion. What does it mean? It means that a substance we burn, 1 mole of substance when we burn under excess oxygen and with standard conditions, we call that standard enthalpy change of combustion. One thing we have to remember that the enthalpy change of combustion are always exothermic. Always exothermic, yeah, always exothermic. Whatever we do, it's always exothermic. Let's say here we have sulfur and oxygen, sulfur in solid state and oxygen in gaseous state. We form sulfur dioxide gas, and that with oxygen, and that what is standard enthalpy change of combustion of sulfur in solid state, which is minus 296.8 kilojoules per mole. Okay, and similarly, when we combustion of methane gas with excess oxygen, we get carbon dioxide and water, and here so therefore standard enthalpy change of combustion of methane gas is minus 890.3 kilojoules per mole. Well, next one is the standard enthalpy change of neutralization. What do you understand by neutralization? It's nothing but that if we react an acid with an alkali in standard condition, that reaction is called neutralization reaction. Sorry. So neutralization reaction we are taking is a aqueous hydrochloric acid and aqueous sodium hydroxide forming sodium chloride aqueous and water. So here we have neutralized it, and after neutralization the product is water, and again here we have a mistake, it should be lowercase 2. Okay, that standard neutralization is minus 57.1 kilojoules per mole. One thing we have to remember that when we do it here, dissolved hydrochloric acid in aqueous solution and sodium hydroxide in aqueous solution, we will see that the reaction is going in with acid and alkali. This is the symbol of acid and this is the symbol of alkali. And therefore, we are getting water. But the sodium here and chloride ion here, sodium ion and chloride ion, they are not taking into part of the reaction. For example, here we get hydrogen plus, chloride minus, sodium plus, hydroxyl minus. So here also sodium plus and here hydroxyl minus here. So therefore we get a chloride ion and sodium ion as expected ions. It does not take part in reaction. Therefore, we write neutralization reaction like this. Okay, next slide. We are talking about standard enthalpy change of reaction. What do you mean by that? We take a stoichiometric reaction, or we call it stoichiometric equation. That means left-hand substance and right-hand substance should have equal mole. So that is standard and stoichiometric equation. We will come to it here. So the reactants and products both must be in the standard state. Remember that both must be in the standard state. And in standard enthalpy change of reaction could be either exothermic or endothermic. So we take an example here. If we react hydrogen gas with oxygen gas, we get water. Here, 1 mole of hydrogen gas with half mole oxygen gas, and we are getting 1 mole of water. The standard enthalpy change of the reaction is then minus 286 kilojoule per mole. Okay, we can write this reaction again. We can write 2 moles of hydrogen gas and 1 mole of oxygen gas. We get 2 moles of water. Then in that case, standard enthalpy of reaction will be minus 272 kilojoule per mole. Like just this is the double. This is the double of this one. So remember, if for 1 mole of water, when we get it, after reacting with hydrogen and oxygen, we have minus 286 kilojoules per mole. But if it is 2 mole of hydrogen, water, it is minus 572 kilojoules per mole. Okay, now we are talking about this all theoretical, but how do we measure enthalpy changes? That is a very important thing. There are different techniques to measure enthalpy changes. In the laboratory, we can see that we can make a calorimeter to measure the standard enthalpy changes of some reactions. And that calorimeter could be as simple as like this, that you take a polystyrene cup and then you have a thermometer, and then this polystyrene cup is like this, and you keep your reaction mixture in this polystyrene cup. And thereby you can measure enthalpy change of any reaction. Okay, while we do so, we do the experiments in calorimeters, we have to use known amount of reactants and known volumes of liquid. Do remember, known amount of reactants and known volume of liquid. That means we measured the reactants, amount of reactants either by valence or if it is a liquid with a pipette where we get the known volume, exact known volume. And if it is liquid, we take it in a standard measuring cylinder where we know the known volumes of liquid. Okay, and what we do, we measure the temperature change while the reaction occurs in the calorimeter. The thermometer we use generally can accurately measure 0.1 to or 0.2 degrees Celsius. Okay, so here we have 480 joules of increase in temperature of 1 gram of water by 1 degree Celsius. The energy required, it is raised by raise of temperature of 1 gram of substance by 1 degree Celsius. It is with this is we call specific heat and symbolized by lowercase c. So the specific heat of water is 4.18 joules per gram per degree Celsius. The energy transfer for a known moles of reactants in the calorimeter is given by this relationship. That is there, it is the relationship. Q is the energy transfer in joules. M is the mass of water in it. And C is the specific heat in joules per gram per degree Celsius. And temperature change, we record in temperature change, which is in degrees Celsius. We have to assume now that there are some assumption we have to do. We have to assume 1 cubic centimeter of water weighs 1 gram. Okay, so 1 cubic centimeter of solution has also measured 1 gram. This is what we have to assume. We make some assumption that 1 cubic centimeter of solution has a mass of 1 gram. The solution has the same specific heat as water. We say the specific heat of water is 4.18 joules per gram per degree Celsius. So here we have the solution. We have also that we take the specific heat of the same as water. It is possible to scale. During enthalpy change per mole of defined reactant product, the relationship we then use as enthalpy change is equal to minus mc delta T. Okay, we go to a problem. So by looking to these problems, we will understand how we measure the enthalpy changes and how we calculate it. So problem 1, what is it? We take 4 gram of ammonium nitrate and dissolved it in 100 centimeter cubic of water. And by this, we notice that the fall of temperature is by 3 degrees Celsius. Then we were asked to calculate the enthalpy change per mole of ammonium nitrate dissolves in water under this condition. We have specified the condition under this condition. So what we get in this, the solution, as we said, the solution's specific heat is as water. So it is solution specific heat of air. It is 4.18 joules per gram per Kelvin. And density of water is given here 1 gram per cubic centimeter. So from this, we can calculate that energy taken is Q is equal to M. M is the mass, C is specific heat, and delta T change. We have mass 100 gram. That means 100 centimeter of cube water is 100 gram if the density is 1. And then this is the specific heat, and then this is the temperature change, which is in Kelvin. Okay, so this is what is 1,254 joules. Now we have to convert it into per mole. Remember that now we have to convert it per mole. So ammonium nitrate, we took 4 gram, and if we divide this with molar mass of ammonium nitrate, we get mole. So molar with this 4 gram, we get 0.05 mole of ammonium nitrate. So energy taken per mole of ammonium nitrate, we have to do this. So 100, this is 1,254 joules divided by 0.05 mole, and that is equal to 25,080 joules per mole, and that is 25 kilojoules per mole. Why we take 25? Because we are experimenting here with two significant figures. So therefore, we have taken this 25 kilojoules per mole. This reaction is endothermic. So the enthalpy change for the system is positive, and that is what it is, ammonium nitrate in solid state. And then we get ammonium nitrate aqueous solution. The enthalpy changes plus 25 kilojoules per mole. So similarly, we can take another reaction, another problem, and see what happens. That in this problem, we are saying that we take 50 cubic centimeters of 2 mole per dm cube hydrochloric acid is mixed with 50 cubic centimeter of 2 mole per dm cube sodium hydroxide in a calorimeter at 25 degrees Celsius and 100 kilopascal. This is the standard enthalpy change. You'll find out the standard enthalpy change for that. Okay, the temperature is, doing this, the temperature raised by 13.7 degrees Celsius. We are asked to calculate the enthalpy change for the neutralization of this reaction. As I said, we are in this. We are given that standard specificate is 4.118 joule per gram per Kelvin, and density of water as it is. With this, we can, and we were asked also to give the answer in appropriate number of significant figures. So, if significant figures are here, this is 3 figures, significant figure. Okay, this is the reaction. And 1 mole acid reacts with 1 mole base. 1 mole acid reacts with 1 mole base, forming 1 mole water. Is it? This is the energy given out due to this reaction of 100 cubic centimeter solution, because this is 50 cubic centimeter, this is 50 cubic 100 solution. So we get 100 gram. This is the specific heat, and then we have this, the energy temperature raises by this. So this, if we calculate this, we get 5,727 joules. Now we have to see the mole. So we have the same mole of hydrochloric acid and same mole of sodium hydroxide. So we convert this. This was 50 cubic centimeter, and then per dm cube, and then 0.2 mole and 2 mole per dm cube. So we calculate this, and we find that it is 0.1 mole. Reaction taken 0.1 mole of hydrochloric acid and 0.1 mole of sodium hydroxide. So now energy given out for per mole. This was the calculation of Q, and then we divide it by 0.1, and therefore we get 57,270 joule per mole. And the significant figure is 3 figures. Therefore, we keep it 57.3 kilojoules per mole minus 57.3 kilojoules per mole. So now we have seen that how we find out or calculate the enthalpy changes of reaction or neutralizations with 2 examples. Now we have to talk about another problem here. If you remember, we say, do you have to make some assumptions? And that assumptions are we are making that this is our experimental condition, and we don't lose any energy, and we don't lose any reactant or product, something like that. But in thermochemical experimental calculation, if we use this assumption, that means if we do not use this assumption, then there will be some error in it. So this open polystyrene cup will lose some energy in the surroundings, and this also. So what are the assumption we have taken, that all the energy from the flame hits the water. But in practice, we do see that all the energy hits of the metal can and the surroundings are. The flame is affected by draughts, or sometimes the fuel burns incompletely, leaving shoot or unreacted materials. These are the problem which causes errors in our experiment. So to measure accurately what we do, we use bomb calorimeter to measure this enthalpy change, bomb calorimeter. That means we have a completely closed system, and if we see here, this is the water containing vessel, and this is what is we call bomb calorimeter, and here is the small dish containing sample under test. Here we have a stirrer, and here we have a thermometer, and this is a insulating jacket. This one is insulating jacket. Oh, this one is insulating lead, and therefore we make the experiments to avoid energy losses as much as we can and burn the reactant, combustion reactant, so that there is no carbon left. So the carbon monoxide or shoots are not produced. So these are the way when we do the experiment, and with bomb calorimeter we reduce the error in the experiments. So generally in I would say AS level laboratory or A level laboratory, they do not supply this bomb calorimeter. It is being used in undergraduate classes, and carefully experiment should be done very carefully, and precautions should be taken. Safety precautions should be taken in these sort of experiments very much. We have been talking about, enthalpy changes and how we measure it indirectly or directly. But in this slide, we'll take an example of a law and see that we can use this law and thereby also calculate the enthalpy changes. This law will take a little bit more, it will take a little bit more time, and therefore we continue this in the next lecture. Thank you very much for your attendance and for being with me. Thank you.